Wow, I cannot begin to express my thanks to the CSD for inviting me to their party, and happy birthday. It's really exciting for me to be here. I've packed a lot of things that I'm hoping to fit in 25, 30 minutes. But it was fun, and it was hard to figure out how can I express my deep appreciation to the CSD, or the CCDC, for what the CSD has meant to me in my research. And I thought maybe I might start with a slide that I commonly use in my presentations to just highlight where in Eli Lilly and Company, where I've spent the entirety of my career, I tend to operate. So we're going to move past discovery into the development phase. And in the role that I have served for the vast majority of my career, where I built the solid state form screening and selection program, we're going to move to where the drug molecule itself has been identified. And our main goal is to figure out how to find ways to pack our molecules into crystal structures that afford us purification, that afford us exquisite control over physical properties so that we can deliver our drug to the patient every time throughout the entire shelf life of the product. And so to maybe frame some of the challenges that I have experienced over the couple decades that I've been doing this work, and to frame it in terms of how the CSD has been important to me, I thought I would craft this slide to talk about the challenges around finding forms. We don't really know if our molecules will crystallize, and we certainly don't know what forms they will crystallize, and we don't know if there will be more than one form, or if any of those forms, for that matter, will be useful to us. And so we expend a lot of experimental effort seeking out forms. And with a lot of work, oftentimes we're fortunate enough to identify different crystal packings, and with a lot of work and maybe a little serendipity, with extra effort, we might in fact realize and appreciate a few other forms. But what has us worried and keeps us up at night are the different crystal packings that we haven't seen. And we don't know if we haven't seen them because we haven't looked long enough, we haven't looked hard enough, we haven't been smart enough. And so this concerns us because we're all familiar with some of the more high-profile case studies where forms have been late appearing and resulted in market withdrawal. So this kind of captures the challenge we are in with respect to how we leverage the Cambridge Structural Database. I can look at it in a couple different ways. One is, how can we assure ourselves that the structures we have realized are what they are? And secondly, how can we get a handle on whether there is a sort of risk for something else creeping up in our crystallization? And so I thought, if this is a little bit of an aggressive agenda for this presentation, but I would like to start with a couple simple case studies that kind of highlight a couple different ways of looking at how the CSD has impacted drug development at Eli Lilly, and then show how we use that information and how important it is in our structure-based drug design to really understand the properties that arise from these structures. And then I'm really happy to talk about some of our recent experiences with the CCDC tools that have been used to assess polymorph risk, and then to follow that up with some recent work that we've done with Sally Price at University College London to look at how we might complement our experimental solid form screening efforts with crystal structure prediction alongside the structural informatics. So with that, I want to show and share an example of how I use the Cambridge Structural Database many years ago, actually, and how this is just one very typical example of how the CSD has impacted us in development. This compound is a prodrug of our orally active blockbuster drug gemcitabine that was under development, and we could never crystallize this molecule. It was presented to me with 2 pKa's that were very high. So it was presented to me as a non-ionizable molecule. And because we couldn't crystallize it, the first effort was to try to make a co-crystal. And so with some effort, we eventually made a 2-to-1 composition with toluene sulfonic acid. And we solved the crystal structure, and the crystallographer presented this crystal structure to me. And so I feel at liberty to tell Terry, wherever you are in the audience, I actually play a crystallographer at Eli Lilly. I'm not a crystallographer. But I've spent a fair amount of time looking at these structures, and for everyone in the audience, this is not going to look like a very sensible structure. It's not going to, even though we know that, or that we were told that this molecule was not ionizable, and of course you have protons in wrong positions, and this contact here is incredibly short, far shorter than what you find in the CSD between guanine and cytosine. So it really made no sense at all that this was, in fact, a co-crystal. And so I presented this information to my company, and it was rather controversial at the time, very contentious, in fact. So I went to the CSD because I needed the confidence that, yes, I think I know what I'm talking about, and they need to know that it's, I have the backing of the CSD in what I'm saying. So I simply did a search of cytosine structures, found 200 structures. This was more than a decade ago, by the way. And out of the structures, a quarter of them had protonated cytosines, 3/4 of them had neutral cytosines. And what I was able to show is that when you had protonation, sometimes you formed the dimers. They were actually hemisalts, so you had a charged neutral and an ionized form. But in no instances out of 153 structures did we see the dimer. And so I was able to take this information backed by the statistics of the CSD and bring that to my organization, and that basically got our crystallographer to take a second look at the structure, re-refine it, put the protons in the proper place. It also caused our organization to go back and reevaluate, change the methodology for measuring pKa's, and in fact there was a pKa that at a very low pH. And this sort of information is great from a scientific standpoint. You want to be right in the data that you're correcting. But there are also practical ramifications for this. Some may argue, well, this is outside the physiological pH range. But the reality is this actually helped us understand some of the pH instability that we had with this compound, recognizing that it was ionizable. It also helped us, if you want to foreshadow today, with the current situation with the FDA's guidance on co-crystals, to learn how important it was to properly characterize salt and co-crystals. Unless we're able to change what the FDA has currently done with respect to the development of co-crystals, it's going to be incredibly important that we demonstrate where our protons are, because it sets a totally different regulatory pathway depending on what we choose. That example showed how the CSD was important based on what you should see in the crystal structure, and I thought as a complement to that, maybe I could talk about what you don't see in a crystal structure. So this compound was a compound that was under development once again a number of years ago, pruvansaren. It was being developed as a phosphate salt, and it was characterized as a hygroscopic anhydrate. We had thermal analysis data which showed that we had about 1% weight loss when we heated this material. For those of you familiar with pharmaceuticals, that amount of water could arise from a variety of different sources. But our moisture absorption isotherm, where you take your material, you subject it to varying relative humidity, showed that the adsorption and desorption curves were not seated on top of one another. So we were not getting upwards of 1% weight. That's really a function of how we ran the experiment. So if we just ran the experiment longer, and even longer yet, you can see that actually we can, if given enough time, absorb on the order of 1% water weight. And so this really gave us enough information to know that water must be getting into that crystal. And it was backed up by variable humidity X-ray. These changes in this unit cell are very subtle. In fact, this amount of water, this 1%, is about 1/3 of equivalent of water. We also had solid-state NMR data that suggested that water must be getting into the crystal. And what was nice about the phosphorus 31 NMR data was that as water is getting into the crystal, as the humidity is raised from 0 to 98%, you clearly see that the phosphorus 31 resonance is being affected, so the water's probably somewhere near the phosphate ion. And that's great information. And historically, when we ended up getting the crystal structure, there was no water to be found in the crystal structure, so nobody believed that me when I said, well, no, really, there has to be water in there. But that's the power of a picture. When you have a picture and it doesn't show water in it, people are going to believe it's anhydrous. And when I would want to show some of the pictures of the crystal structure, there was no way you could actually look at the structure and see open pores. But now, with some of the tools that we can use, we have the ability to look at void spaces. And you can very clearly see where the water resides. And you can also see a really nice proximity to the phosphate anions. And if you want, you could probably envision some sort of hopping motion that helps you understand and visualize the properties that we're seeing and rationalizing and creating the picture that we see. So between these two examples, I wanted to highlight one where it's what you see in the crystal and it's what you don't see, and the fact that we look both at what's there and what's not there in our analysis. Now I want to turn to another case study that goes beyond getting your crystal structure right and looking more at polymorph risk assessment. This is a compound that is currently under development. We're really excited about this compound, Evacetrapib, and has a nice, interesting story that I was grateful to my company to allow me to talk about. This compound would not crystallize for us at the point in time shortly after the compound was nominated. I don't recall a compound in my 20-some years that we have tried that hard to crystallize, and it just would not crystallize. And so we finally got to the point where we realized that we're probably going to have to develop an amorphous dosage form here, even though we really didn't want to. And there are other issues to go with that. And so we continued with the development of an amorphous form, but there was still some solid state screening going on. And within 1 week of this compound being nominated, it finally crystallized. And this is not what it first finally crystallized. These are optimized. That's after optimization. But it crystallized in a failed attempt to make a formic acid solvate co-crystal. And it only crystallized then because we crystallized from methanol. And we're familiar with a lot of cases where failed salt and co-crystallization attempts yield a new form. But methanol was also important in this story because methanol was a precursor to this monohydrate crystal form that we finally obtained. And we had performed this crystallization many, many times on varying ranges of purity material. This just shows what happens to the crystal structure that we initially crystallized, being a methanol solvate, and how we could rationalize the water coming into this solvent, and a slight decrease in the unit cell parameters to where we formed a reasonably stable monohydrate composition. Now, we were really happy. This actually represents a breakthrough when it comes to the development of our compounds, because now we have a purification pathway, we have a delivery and a stability pathway, all the benefits of the crystalline state. So we were exceptionally happy about this. We did run into some issues with this exchange process and preserving some crystallinity. So we ended up, now that we have seed crystals, developing a crystallization process from isopropyl alcohol, which would directly crystallize it. So this was an example where we were, seriously happy about this. We're also in the process of working through the Crystal Form Consortium at looking at how the structural informatics tools developed at the CCDC can help us understand the risk for polymorph assessment. And so if we look simply at the hydrogen bond coordination, and I'll step through a couple of these ways without going into the details of the numbers, what you can see is that there are a couple places where you have a lot of propensity, if you will, or coordination likelihood in this case being satisfied, but you also have a few instances where maybe things aren't so great. We didn't have this at the time we were doing this work, but certainly looking at this, we would have motivated us to continue our form screening. Nonetheless, we were motivated anyway, and it was a good thing. And I'll show you in a second. In terms of the hydrogen bond propensity, one of the things that we found was really interesting is water actually probably preferred interacting with itself. That was kind of interesting. But generally speaking, we had reasonably high satisfaction of the hydrogen bonding groups. And if you look at the fins, this was interesting to us. This molecule is overloaded with hydrogen bond acceptors, or so I thought. And what you can see is the hydrogen bonds that do form are reasonably well satisfied from a geometric standpoint. But what you also see here is that many of the nitrogens the Cambridge Structural Database doesn't see as being good acceptors. So the imbalance of donors and acceptors was not as high as what I thought it might be. Moreover, one of the other good acceptors appears to be sterically hindered based on the molecular conformation of the molecule. So we're looking holistically at these risk assessments. We certainly would have continued our search for solid state forms. And in fact, once this material crystallized, once we had the monohydrate as a starting material, we could crystallize all sorts of forms. In fact, many of them were actually structurally related, as you can see here. And for us, we were lucky because really only one of them, stood out as the crystal form that we could develop. So we continued along that pathway and had beautiful crystallization developed from isopropyl alcohol. And we went ahead and scaled it. This is a very large volume molecule, and so we were making hundreds of kilos of batches. And we had great success until about 5 years later. This is batch 13. 5 years later, these crystals don't look like the crystals that we had been developing, that we came to understand. These crystals look far worse. And in fact, this ended up being a new polymorph, form 1. And I can assure you, 5 years after you looked, you don't want to be finding new forms. And for the people who tell me that it's obvious, trust me, there was a lot of consternation. We would have happily looked, had we known how, to find this form. In the end, this form ended up being a blessing in disguise. We didn't have to deal with dehydration. We had good purification, excellent properties, and we ended up switching to this form. And so it really solved a lot of problems, but there was an unbelievable amount of consternation. So when the companies like the Abbott's or the AbbVie's tell you that you see that they have ritonavir, and UCB has rotigotine, my guess is that most of our companies have stories. This is probably the closest we've gotten. So how about the form 1 structure? Now we see that our form 1 structure has no water in the picture, of course. And we see some instances of high hydrogen bond coordination, as well as some maybe not so satisfactory. I'm not so sure that this separates the monohydrate from form 1. Likewise, with the hydrogen bonding propensity, now we don't have the water in here, and you see that honestly there's a spread of propensities, and we're on the higher end of that, but it's not overwhelming. And the other thing I would point out is the model that I made is based on a statistical analysis of these functional groups, not of all which are terribly highly represented in the CSD. So the model's only so good as well. We have to recognize that. But I would say that we're probably on the order of where we felt we were with the monohydrate based on this assessment. The fins ended up kind of being interesting because we also had reasonable geometries for our interactions. But what was interesting was this N23, which was supposed to be sterically hindered, and you see there's no hot spot. This molecule was added after the fact. We thought that was sterically hindered, but in this late appearing form, it must have had to slide those molecules in just so to be able to fit that. That's not a predicted interaction. So you can ask, could that have been one of the reasons? And in fact, we did ask reasons. When you have a lot of consternation in your organization about a late appearing polymorph, your organization and your management is going to be asking you why. And then they'll mumble under their breath, what's wrong with the solid state group, right? Well, we asked ourselves why. We asked ourselves, did we not screen for solid forms? Was that not complete? And I think we can never say never, right? I think we can never know. But what I can tell you is in the course of the 6 or 7 years that we worked on the compound, it had been crystallized under similar conditions many, many times. How the new form appeared was a mechanical failure in production, which allowed the slurry to be held for a very prolonged period of time at all of 60 degrees. And that was what caused this material to happen. Is there a conformational change that was required? Well, I don't think so. I don't see this form 1 conformation being really that different from the monohydrate, and we've got other evidence that we're not perhaps limited by the molecular conformation. What about a different impurity profile? Well, based on the observation of how this form suddenly appeared, I would have to say that that is a very likely source. What happened at 60 degrees? And then finally, prolonged exposure. I think that goes also. It probably didn't hurt. Now, when you're talking to your management and they're asking you why, and you're using very qualitative terms like this, it's a very uncomfortable conversation. But we're not yet at a point where we can start predicting what a molecule like Evacetrapib is going to do. And that's going to allow me to segue into the last part of this conversation, which is, what if we could predict what the packings were? We, like many people in this room, have been following very closely the progress of the CCDC-sponsored blind tests. And when the 5th blind test was published in 2011, I personally got very excited about molecule 20. And the molecule was solved by 2 groups, one of which was Sally Price's group. And it was after that point I called Sally and asked her if she would be interested in collaborating and testing out some of our LY molecules in exchange for having access to bodies of experimental solid form screening results. And so the molecules that we've worked on, this is the first set, and I won't talk about all of these. I'm going to simply, for the sake of time, present some highlights here. I'm going to focus just a little bit on tazofelone, which some of you at the CCDC have heard about. And then this pair, where we've essentially conserved most of our hydrogen bonding, have been contrasted together as well. Our evaluation was not a blind test. Blind tests are for the CCDC. We wanted one where we could simulate what real-world development would be, where we know of some, possibly a lot of information on the solid forms. We wanted to see how we could fold that information in simultaneously. So let's jump over to tazofelone. This is Sally's crystal energy landscape, and this is probably the best case scenario. This is the scenario where the forms that we have found, whether they're Z'(1) forms, which would be found in the search, or Z'(2) forms, which are not in the search, all represent a good chunk of the structures in the low energy region. So for those of you who are less familiar with the crystal energy landscapes, each dot represents a crystal packing ranked by the lattice energy and the packing efficiency. In the best case scenario, you have low energy, highly efficiently packed crystals, and that's a good thing. And so this was really great, although I will tell you, when you have a compound that you think you know a lot about, and then Sally shows you all of the things you haven't found, it is rather nerve-wracking, right? But what she has been able to see, in addition to the ones that we have, were different packings that have some strong structural similarities. And that was interesting. You can kind of see it from how I've shown these unit cells. 3 of our racemic polymorphs, in this case, look to have layered structures. It turns out there are other structures that Sally has predicted at low energies that also have these layered structures. And in fact, this underpinned some of the work that we eventually did to show that the crystal forms of tazofelone are, in general, the racemic ones this is, are defective. They all have domains and inner growths, and in fact, that was borne out initially by our DSC results that we collected on single crystals, where we simply couldn't single crystal to single crystal reproduce our results. And it later was shown to be the case through analysis of the raw diffraction. So this looks much like aspirin and some of the other notorious examples. But how did tazofelone fare with respect to the informatics? How does that factor into this? We did an analysis of the hydrogen bond propensity, and I would say generally it looked pretty good because we were able to show, relative to what we knew the stability to be, that the racemic polymorphs tended to have higher propensity hydrogen bonds than the less stable single enantiomer. And we could also, because we coupled this with crystal structure prediction, roll in the predicted packings into this analysis as well. One of the limitations, however, and I know Joel and others have pointed this out, is that when your hydrogen bonding is conserved among your polymorphs, obviously you can't tell the difference in the hydrogen bond propensity. The FIMs actually were really interesting for us because this gave us just the beautiful power of looking at where your hydrogen bonds are mapped onto the molecule relative to where they appear to be statistically favored. This allows us to see some of the compromises that our molecules make in trying to form hydrogen bonds of any kind. And this has been a really great sort of tool for us, not just for tazofelone, but for a variety of other compounds that we've put to the test. But I would say, generally speaking, the informatics gave us some very useful and complementary information. The last comparison I want to make by way of examples are our contrast molecules, which we affectionately refer to as B5 and DB7 because they have long chemical names and they never were given a shorter, complicated name. These two molecules are certainly structurally different, but as I said, the side chains are relatively conserved and they crystallize entirely differently. B5 is monomorphic, and as you can see with DB7, we have a whole host of crystal forms, including neat forms, hydrates, solvates, amorphous. Some of those forms allow us to expand our screen as well. What you can see from the two crystal energy landscapes is one of the molecules in general has a much better propensity to pack in dense structures than the other. And if you look really closely, you'll find out that despite the conserved hydrogen bonding, one of the molecules tends to form low energy structures with intramolecular hydrogen bonds and the other with intermolecular hydrogen bonds. And these sorts of things wouldn't be predicted. With Sally and Doris Brown's help, we were able to come up with a structural model. Actually, they were able to do that for one of the compounds that we could not get single crystal structures of because this was a dehydrated species. But what you can see here is in this comparison, if you're looking, and here's your Z prime of one answer, if you're looking at whether you would expect monomorphism or polymorphism, you're not seeing a decided difference between these two. And so it's what we're learning in the process of this research collaboration is how to interpret these crystal energy landscapes in light of what we are seeing experimentally. Now, how did the informatics do? So in this particular instance, we have hydrogen bonds of the intramolecular variety being heavily favored. And in fact, in the most and the only form of B5 and the least stable form of DB7, that's in fact what we see. But the most stable forms actually don't track with the highest propensity hydrogen bonds. And so this is exactly what we want to share, that I think hydrogen bonds are fantastic to look at and rationalize crystal form stability in terms of, but obviously there are a lot of interactions that make up our molecular crystals. And so in some respects, I'm kind of happy to have examples that show how well it works and where the areas of opportunity are. I just want to give a shout out with respect to the DB7 compound to some work we did around the hydrates and bring myself back to the very first example. Because in the DB7 compound, we have two hydrates, one of which is a stoichiometric hydrate, retaining about 2 molar equivalents of water in the structure. And the other one, if you look closely, is a nonstoichiometric hydrate. And if we come back to the solvent pores, much in the first example, what we find is our nonstoichiometric hydrate does not have continuous channels. These are pockets that as you remove water from this crystal, the unit self-contracts, and the pockets become actually farther and farther apart. And so what happens is when you get to the low end of the humidity range, it becomes increasingly difficult to pull those molecules out. And this is a behavior that we ourselves wanted to interpret in terms of structural behaviors. We have seen exceptions to this rule. There are some in the literature. Probably more surprising to us was the stoichiometric hydrate, though, which showed that the water actually resided in open channels. That's a very unusual situation. And I won't spend, for the sake of time, any more time on this. The paper, which is in the next slide, the one after that, is cited in the next slide. What I would like to do, though, is wrap up with trying to put it all together with respect to solid state form design. Obviously, we're given some fairly interesting molecules as substrates to work on. They're all interesting. But what we're finding is that in order for us to be able to create and aspire to structure-based solid form design, we're going to need all of these components. And usually it gets kind of murky before you get clarity. That's when you know you're done. But it's all important. And so with that, I'd like to give a shout out to my research team, now my former research team, who has stuck with me on a lot of these compounds for many years. A special thanks to Sally Price and her team for the great collaboration, for her ability to teach me so much more about molecules I actually thought I already knew a lot about. It's been absolutely incredible. as well as to the CCDC, being members of the Crystal Form Consortium, and Neil Feeder, who sat with us patiently through our tazofelone crystal structures, and then some of Sally's collaborators as well. And with that, I thank you for your attention.